Thanks, John. Well, I'm Peter Singleton. I recently retired from the U.S. Forest Service PNW Research Station in Wenatchee, Washington, and it's really great to be able to come in here and help present these results from the Southwest Washington Cascades to Coast analysis. It's been a great bunch to work with, and I think we've got a bunch of useful and exciting stuff to share with you all. Can I have the first slide there, please, John? So the background for the Washington Wildlife Habitat Connectivity Working Group is to really sort of follow up on a lot of the basic principles that Gary was presenting in the last presentation. And it's always great to follow Gary and folks like that really can provide the framework for understanding what it is we're trying to achieve with this. And I think John's question about that, top down versus bottom up nature of this work really gets at the spirit of the Washington Habitat Connectivity Working Group. Here you can see here the mission statement of promoting long-term viability of wildlife populations in Washington through a science-based collaborative approach that identifies opportunities and priorities to conserve and restore habitat connectivity. I think to me the key words in there are science-based and collaborative. This has been a group of folks from across agencies and non-governmental organizations, tribes, academic institutions, and just citizen volunteers that have stepped up and really wanted to be involved in developing this mission. And it's spanned conservation activists and academics and managers and lots of individual species experts that have come together to produce this. And so, one of the great things about the Connectivity Working Group is it's kind of been an exercise in social engineering to really bring together this network of people that are interested in this topic and provide the opportunity to complement each other's skills and develop this vision. One of the things that I really noticed in pulling together this slide particularly is this set of faces in this Connectivity Working Group photo here. That photo was taken at the Federal Highways Administration Awards ceremony. And most of those folks have moved on to other roles. And now we've got a whole new generation in the Wildlife Connectivity Working Group that's moving this work forward. And I'm really optimistic to see this stuff continuing to go forward as I step back and as other people step in and keep it going. So let's move on to the next slide. So one of the goals with the Connectivity Working Group was sort of to take a multi-scale approach to assessing connectivity. The need for the Connectivity Working Group really emerged from work that was conducted in the late 90s along Interstate Highway 5 through Snoqualmie Pass, and that was the area where several of us started working on looking at assessing wildlife movement patterns and developing landscape permeability models that could identify areas for highway mitigation at Snoqualmie Pass. And when we found that we were able to develop those models and do some on-the-ground validation, they actually worked pretty well in that yellow circle in the middle there that you see. We kind of stepped that up, and Paul Wagner from the Department of Transportation and others really helped support that work of stepping up to an eco-regional scale, and then we were able to run these larger models, and eventually that evolved in 2007 into the larger working group that was able to develop this statewide analysis, which took on all of Washington State for 16 focal species in a landscape integrity model. And then with that broad overview, we were able to develop kind of an umbrella vision and highlight areas that needed not really more work, but finer scale work and more refined modeling for questions, to identify local questions and things like that. And so the first place that we stepped down in scale into was the Columbia Plateau, because that had really interesting, unique ecological shrub steppe issues that weren't as well addressed by the forest dominated models. And then we stepped up into the transboundary area through the northern Okanagan into British Columbia and the border with Washington, that blue circle there. And that was more of sort of an interpretation, collaborative vision development process, integrating managers on both sides of the border. And finally, another place that we identified a real need for unique models and questions was in Southwest Washington, in that green circle that then became the Cascades to Coast analysis area. Now, the thing about the Southwest Washington area is that it's really different than a lot of the Cascades or the Columbia Basin. There's a unique history of land management there. There's a pattern of forest road development, but not as widespread access as maybe in some of the public lands. There's sort of unique land use development pressures in there. So we really felt like the statewide models really didn't do service to all the processes we really wanted to understand in that landscape. So that led to us stepping down into Southwest Washington and doing this Cascades to Coast analysis. So next slide. So the work that the Washington Connectivity Habitat Working Group has done has really been built off of this core corridor connectivity model. There are other ways of looking at habitat connectivity. There's sort of whole landscape approaches and things like that. And I want to give a shout out that this isn't the only way to do things. These are the tools that we've developed for the Washington Habitat Connectivity Working Group. They're getting really widely used now through the linkage map or GIS tools that we've all been involved in developing through CircuitScape. And so there are lots of places that are using these, and they're very well established methods, but it's not the only way or the only good way to do this. And there's several steps that are involved. First you have to understand what the pattern of habitat is. And then we translate that concept of habitat into sort of a concept of resistance to movement. Basically, it's the inverse of habitat here. You can see those red areas in that upper right panel are the areas that are hard to move through, reservoirs, agricultural lands, residential developments. The green areas are the patches of pretty good stuff, the forested landscape in this case. Then we can turn that into a model of core areas that we want to connect, that lower left panel that shows those purple blobs of relatively good habitat. And using that resistant surface, we can figure out how accessible the surrounding area is for animals that might be moving from those cores. Those dark blue colors are things that are going to be pretty accessible for animals based out of the purple because it's pretty contiguous forest. And then it goes across a gradient where it becomes increasingly resistant, increasingly less permeable. And you can see the brown and yellow blobs there that really correspond to those reservoirs and the urban areas that are in that upper satellite image. Then we can slice and dice things a little bit differently in that lower right in that lower right panel to translate that into the most optimal linkages and the surrounding corridors. Now, one of the really important take-home messages that I think is important for people to understand in those bottom two panels is that there's not, all this stuff is really fuzzy. We don't really know where the cutoff is in terms of what an animal, an individual animal or a population will really be able to get through. Okay. And we're, as managers and as society, we always want to look at this binary map of polygons that says this is a corridor and this is not. But in reality, our understanding of that and the variation in individual animal behavior or populations really, doesn't work well in that binary landscape. So one of the things that's underlying all the maps that you'll see here is this sort of continuous map of relative permeability and relative linkage value. Okay. Eventually, we sort of get pushed into the corner of having to develop binary maps and having to say this is in and this is out, because that helps us prioritize and helps us understand things. But I want you to all understand that there's this underlying continuous mapping product as well that folks that are local users can dig into and these relative values that we have. Next slide. Okay. The other thing is that, these are models. Models are systematic symbolic representations of something else. Okay. And when we develop a model, often we can make it too complex. Okay. We've already got the ultimate complex model of ecosystems, which is the ecosystem itself, but in order to really understand what's going on and to make decisions about the process, we need to simplify things down to a level where we can really address the question at hand. And I like this example of the smiley face versus the Picasso. Depending on the question that you're trying to get at, sometimes the smiley face is a little bit more effective than the Picasso. I'm a big Picasso fan. I think it's an incredible piece of work. But when we're really trying to understand basic stuff, sometimes we have to make really substantial simplifying assumptions and focus on how to reduce the question in order to get the information that we need to act upon. All right. So throughout this, modeling presentation, I think you'll see places where we've had to make professional judgments or had to simplify things in order to make it simple, make it understandable. But maybe this simpler is better graphic will help you understand why and how we get to some of this. Okay, next slide, please. Okay, so the steps in our connectivity modeling process are first to select the focal species that represent the key processes and threats that we want to address. Okay. Now, often folks see that we modeled, in this case, 6 different species, and they think, well, that's the connectivity for that species. But what we've done is try to really hang our hats on carefully selecting those species and making sure that we select species that are representative of important processes or ecosystems or habitat types or threats that we want to understand. Okay, so that process of selecting the focal species is really quite involved and quite thoughtful, and helps us understand and compare things beyond that. In addition to the 6 focal species, we also have done a landscape integrity modeling approach that allows us to sort of evaluate the connectivity of natural intact landscapes. So for each one of those focal species, we map the habitat. We identify those purple core areas like the last graphic. We evaluate the landscape resistance in the surrounding landscape. We calculate the permeability using a cost-weighted distance algorithm. We identify linkages using least cost paths and identify corridors using least cost corridors, and identify barriers and other network characteristics. Once we run that for each one of those focal species, and if you're interested in specific information on each one of those steps and what each one of those things is, I'd refer you to the circuitscapes.org website that has the linkage mapper tools and has the support for that. Once we develop those connectivity maps for each one of those focal species, we can categorize them and develop composites that sum the important network areas, and then use network metrics to develop linkage prioritization. So next slide, please. Okay. So as I mentioned, in that focal species selection process, we wound up focusing on 6 focal species plus landscape integrity. Cougars were selected to be sort of a habitat generalist that moved long distances, that were sensitive to human development, but would move through a variety of habitats. Fisher were selected as our old forest species that was really sensitive to to sort of distribution of mid-elevation structurally diverse forest. We really wrestled with the early cereal young forest associates, trying to find a specific species that we could hang our hat on for modeling connectivity for low and mid elevation. Early cereal forest was sort of challenging. And finally, we settled on mountain beaver as a good sort of low mobility species that was associated with early cereal species that we could look at that. Western gray squirrel was our low elevation oak woodlands species. We developed a real interesting model for American beaver to look at riparian and aquatic habitat connectivity. That's going to be interesting for some of the fisheries folks, but remember, beaver can move up and over upland areas, so it's not going to be redundant with the fisheries connectivity model. And then finally, we did the landscape integrity, which just looks at the effect of human impact on the ability to move through the landscape. So next slide, please. Okay, so here's our analysis area. We bounded it by the northern border of Pierce County over to the Cascade Crest, down to the border with Oregon and out to the coast. We did not take on areas north of Pierce County because that gets into a real urban and suburban development dominated landscape that really warrants a different kind of approach, a different group of people, and a different scale of analysis to get on to really wrap our heads around what might be important for connecting those urban and suburban landscapes. Our goal was really to look at what the broad scale patterns were down through this Cascades to coast ecoregion, and look at the patterns through southwest or Washington there. Next slide. Do we have next slide there? There we go. So here's the example of the Fisher habitat model here. For the inputs to this, we compiled a variety of GIS layers that were available, including land cover, forest structure, roads, human development, elevation, and slope. These similar inputs were used for all 6 of the species. I'll just use Fisher as the example here to run you through what we've got. So here you can see the dark green areas are the good habitat, lots of forest associated with public lands in this area. And then the yellow and orange areas are areas of sort of reduced habitat quality in areas that have less structurally diverse forest and more development. Next slide, please. So these same inputs then go into identifying the core areas that we want to connect. So these cores were based on spatial and habitat quality thresholds that would be likely to support individuals or populations of each of the focal species. So you can see here in the case of Fisher, we've got big patches along the Cascade Crest and in the Olympics, and then sort of a set of smaller patches that might help create stepping stones in some of the private forest lands in Southwest Washington and around Joint Base Lewis McChord. Next slide. Okay, once we have that habitat layer compiled and those inputs put together, we can start looking at how bad the habitat is. So this is sort of the inverse to habitat suitability. Okay, you can see the areas here, where you're getting out into the urban areas and some of the water bodies and some of the high elevation alpine areas. They start accruing very high resistance scores, whereas the good habitat gets a score of 1. All right. Now, what happens here is that in this cost weighted distance algorithm, we multiply the Euclidean distance for each grid cell on the map times the resistance value. Okay. So in cost weighted distance, the cost weighted distance of moving across a good habitat cell is 1 times 30, because we're using the 30-meter cell size, all right, versus the resistance of moving across a really bad habitat cell can be, 30 times 50 or even 1,000, or even in this case up to 3,000, where you have really resistant multiple features that effectively are barriers on the landscape. Okay, and then we sum those distance values across the landscape to evaluate the cumulative cost weighted distance to evaluate the accessibility of areas. So that's the next slide here. Okay, so once we start looking at cost weighted distance, this can really be kind of interpreted as a topographic map of where we think animals are likely to be able to get to here. Okay, you can see these different themes radiating out from the cores, and the areas that are in darker colors are the most accessible portions of the landscape, and the areas that radiate out into yellows and browns are the more resistant barrier areas. And I noticed a comment there that maybe not everybody knows what a fissure is. A fissure is a member of the weasel family. Yes, Pinacchia pinati. And so they're actually kind of a medium mobility weasel mastella that has recently been reintroduced into this landscape and is a species of conservation interest. So here we can see these dark areas or places where movement's likely to be pretty random in this landscape. But once you get out to those yellows and browns, they're hitting a lot of barriers, and they're hitting a lot of obstacles to movement in this landscape. And so these are those sort of lower permeability, more resistant areas are going to be places where we're interested in identifying the potential linkages and maybe thinking about mitigation or conservation. So next slide. Okay, so once we have that cost weighted distance, we can do some GIS tricks and look at the least cost paths between all of those core areas. And this is, these least cost paths, these green stripes on here are really, they're bookkeeping devices. They're not going to be real live paths of animals. I mean, ideally, if the animal had full knowledge of the landscape and was optimally moving through the landscape, maybe they'd follow those paths if we have precise and accurate GIS layers. But that's not how animals works. Our GIS data isn't that good. But what these do provide is these linkages provide us a way of developing a tabular database that can have lots of different attributes that we can use for sorting things. Next slide, please. Okay, what gets more interesting? Oh, so yeah, these are some of the attributes that we can use on these linkages. We can use things like network centrality here, where we show those linkages in the darker colors are more central to the network. So those darker linkages are likely to be more important for keeping everything connected than the lighter linkages, where there are lots of different redundant linkages and they don't really connect the central nodes in the network. Those are sort of more peripheral linkages. So it's those centralized high network centrality linkages that are most important. So next slide. Okay. And once we have those linkages identified, we can run sort of a buffer around those linkages and look at what adjacent areas have similar permeability, and start thinking about this for determining corridors. Okay, next slide, please. Okay, so this is the step in the process that makes me the most nervous. This is the part that I feel like I hate to be pushed into the corner of having to do, where we take that nice, sort of continuous map of corridor permeability around those linkages, and we have to at some point say, okay, this is in and this is out, and we turn that into a binary map for each one of the 6 focal species. In this case, in this analysis, we used a 5 kilometer wide corridor width for all the focal species to identify what was in and what was out of the corridor networks. Next slide, please. Okay, and here you can see all 6 of the networks that we developed for each one of the focal species and landscape integrity using those same steps. Okay, so these are the binary maps from each one of those model runs. Next slide. And once we have those binary maps, then we can overlay them and start looking at where those networks are overlapping. Okay, so here you can see the dark blue places are places where connectivity or core habitat occurs for more species, and then you get out to the light green and gray where there are fewer overlaps. Okay. Now note that there's no place where all 6 focal species networks overlap here. There are some that are mutually exclusive. For example, mountain beaver and western gray squirrel don't overlap. So that's why we get to a maximum sum of 5. So next slide, please. Okay. Now here we can start prioritizing those corridors based on some of those linkage metrics that we talked about before. We're interested in prioritizing linkages that are short, that are easily permeable, that are more central to the network, and that connect good habitat. Okay, we can then use the highway system to sort of stratify those linkages and start prioritizing sets of linkages along that intersect major highways. Now, the thing about the highways is that the highways are good features because they're often central in developed landscapes. All right, it's not just the highway, but it's also the Walmarts and McDonald's and real estate developments adjacent to the highways that drive permeability. So next slide, please. Okay, once we do that, we can use this prioritization scheme to highlight those overlapping patches. And here you can see our priority linkages based on places where more than 2 species overlap. And then we can also refine that by looking at the traffic volume in those highway polygons. And you can see, there's a bunch of areas in the Cascades and along the Olympics where they're priority crossings, but they're really broad. And they've got really pretty low traffic volumes relative to other areas. But you compare that to the stuff along Highway 12 going out to the coast from Olympia, and along I-5 going north-south down towards Portland. And those are the places where we really see high traffic volumes intersecting with these multi-species linkages that are going to be most important. So next slide, please. Okay, we can zoom in on some of this stuff and start looking at those priorities. Next slide. Okay, and this is what it looks like on the ground, all right, or at least in a higher resolution. You can see there are a bunch of, there's several important linkages across I-5, north of Chehalis, between Centralia and Olympia, and then in the Joint Base Lewis McChord area and along Highway 12. Next slide, please. And we can also zoom down toward a little bit further south on I-5, and next slide. And we can see some of the important linkages there down by the Cowlitz River and down towards Longview that provide those multi-species connections. So next slide. And this all fits into this sort of broad scale connectivity vision for Southwest Washington. What we see from this is this broadly connected mid-elevation pattern that we're starting to call the Olympic arc on the west side of the Olympic Peninsula that connects down to the southwest arc through the Willapa Hills. And then there's South Cascades area and the Central Cascades area that are all relatively connected. The big fracture zone between those, of course, is the I-5 landscape, where we've identified 3 interesting linkage areas. sort of between Olympia and Centralia, and then down towards down towards Vancouver, and then also the Highway 12 west between Olympia and Aberdeen, and Highway 12 east between Centralia and out towards White Pass. Those are the areas that really are highlighted by this analysis as intersecting with the major highways, and we're able to provide prioritizations within those areas. So next slide, please. So I think that's it. That synthesis map is available in the final connectivity report. And I'll let Alan take it from here to talk about what products are going to be available online and how you might be able to access some of that stuff.